Good evening to all. Today we are going to start with a few topics in Laplace transforms what we left yesterday, and then we are continuing, followed by either vector calculus or before that, if any, before that, in the depending on this topic, I may go to discuss multiple integrals. Okay, if I start multiple integrals, after that vector calculus, or if I start vector calculus first, then I will discuss multiple integrals later. So this few topics left in the Laplace transform are convolution theorem, the convolution or faulting of two functions f of t and g of t for t greater than or equal to 0, or actually Laplace we discussed like this, not required to write. Convolution theorem in Laplace transform, f of t and g of t is defined as f of t star g of t is equal to integral 0 to t f of u into g of t minus u du, and this is further simplifies to a t term denoted by h of t. So this is the symbol star stands for convolution or faulting, which is means that twisting. Okay, so f of t star g of t is defined as integrating with respect to u having the limits 0 and t, f of u g of t minus u. Okay, and Laplace of this convolution, that is called convolution theorem in Laplace transform, L of f of t star g of t is equal to product of their Laplaces, L of f of t into L of g of t. Also because of inverse transform, the same convolution theorem is also defined in, is also given in inverse. L inverse f bar s, it is useful to find the inverse Laplace transform of product of two s terms, where is first is f bar s and g bar s is the second function, is equal to 0 to t f of u into g of t minus u du, and this is nothing but already given f of t star g of t. So Laplace of convolution of two functions is equal to product of their Laplaces, and in inverse it is useful for inverse of a given function where the given function is written as the product of two known functions of s. One is f bar s and other is g bar s. What are these f bar s, g bar s? I told you known methods of not known methods, known functions of s. The meaning of known functions of s, they are the Laplace transforms of some functions f of t comma g of t respectively. Okay, f bar s is nothing but L of f of t, and g bar s is nothing but L of g of t. problems. One. This is given 2011, 2 marks. Given two continuous time signals x of t is equal to e power minus t and y of t is equal to e power minus 2t. Which exist for t greater than 0, comma, the convolution z of t is equal to x of t star y of t. Comma is. Now just observe the given the three functions x of t, y of t, the convolution of these two denoted by z of t, but already we denoted the order, consecutive order f of t, g of t, h of t. Just observe this notation. Only notation changes. Everything is same. Solution z of t is equal to convolution of two function x of t and y of t, and this is defined as 0 to t f of u into g of t minus u du. Okay, so in this, here f and g are nothing but our x of u and y of t minus u. Instead of f and g, it is given x and y functions. Okay, so in this x of t, y of t, first replace t by u, in the second function replace t by t minus u. This is equal to 0 to t e power minus u into e power minus 2 into t minus u du. So with respect to u, t term is constant, keep the outside the t terms, e power minus 2t 0 to t, integral 0 to t, the remaining u term simplifies to e power u du. So this is e power minus 2t integral e power u is e power u, limits 0 to t. After substituting lower and upper limit and multiply with e power minus t, this simplifies to e power minus t minus e power minus 2t. So in this signal, the convolution of the two signals is nothing but, in this problem, difference of the two signals respectively. And one more example, which is asked 2000. Another example, 2000. Given that GT stands for given that L of f of t is equal to s plus 2 by s square plus 1 and L of g of t is equal to s square plus 1 divided by s plus 3 into s plus 2 comma h of t is equal to integral 0 to tau f of tau into g of t minus tau d tau. Comma L of h of t is equal to how much? Now look at this in the second problem. A convolution h of t between f function and g function is given. In terms of u, our original u, it is given tau notation. That is the only variable changes. What is the question requires? L of h of t. So that is Laplace transform convolution theorem. L of f of t star g of t is equal to product of their Laplaces. Here h of t is nothing but convolution of two functions f of t and g of t, which is given indirectly, that is integration 0 to tau. Okay. Solution. H of t is equal to integral 0 to tau f of tau into g of t minus tau d tau. So this is nothing but f of t star convolution of two functions f of t star g of t. Okay. So therefore L of h of t is equal to L of f of t into L of g of t, Laplace of product of their Laplaces, and this is both are given, just multiply, which gives 1 over s plus 3. Next, initial value theorem. Okay, limit t tends to 0, f of t is equal to limit s tends to infinity, s times f bar of s, comma, if f bar s is proper, and instead of asking this initial value of f of t, that is f of 0, this is also denoted by f of 0 plus or f of 0, t greater than or equal to 0, t just like. So what is f bar s is proper in the f bar s, that is proper fraction. Proper means proper fraction, numerator degree less than denominator degree, then only this theorem is applicable. That means suppose we don't know f of t, but the question requires f of 0 plus or f of 0, that is initial value of f of t by taking t is equal to 0. So without f of t how can we evaluate? But in that case its Laplace is given, Laplace of f of t, that is denoted by f bar s. Then apply this result. Okay. Final value theorem, and the same topics will also come in signals and systems paper. Okay. Limit t tends to infinity f of t is equal to limit s tends to 0 s times f bar of s. And this left side is also denoted by what I am highlighting, or simply find f of infinity, infinity minus, like that. Okay. If the poles of f bar s lies on the left hand side of the S plane, either one dimensional plane or two dimensional plane. S plane means if it is only S value real number, then it is one axis, one real axis. If it is S is imaginary complex number, then it can be plotted into the organoid plane, that is coordinate x axis and imaginary axis. Okay. Real axis and imaginary axis. So what is the generally poles? These things will again come in complex variables. Don't worry about this word. Poles means, just for understanding purpose or for time being, that f bar s, if it is a fraction, then it is going to, that means generally a function is not defined where, provided denominator equal to 0. Whenever a denominator equal to 0 at a given at some value of s, then at that value of s, f bar s is called not defined. And for understanding purpose, for these problems we are saying that the values of s where function is not defined are also called here poles. That poles should lie on the left side of the s plane only. Okay. For example, your denominator is 1 over s minus 1. I mean your f bar s is 1 over 1 by s minus 1. This 1 by s minus 1 is defined everywhere except at s is equal to 1. At s is equal to 1, this is going to, denominator going to 0. So I can say that s is equal to 1 is a pole. So go to your organ plane, that is s plane. S is equal to 1 lies on right side to 0 origin, that is right hand side. So this theorem is not applicable. Suppose 1 by s plus 1, that function is, the poles are given by denominator equal to 0, that is s plus 1 is equal to 0, s is equal to minus 1. So s is equal to minus 1 is a pole of the given function 1 by s plus 1. So that minus 1 belongs to left side of the origin. So it lies on the LHS of the S plane. Okay. So in that case, final value theorem is applicable. See example. One. 2010, given L inverse 3s plus 1 divided by s cube plus 4s square plus k minus 3 times s. Full stop. If limit s tends to if limit t tends to infinity, f of t is equal to 1, then k is equal to this is given 1. So here limit t tends to infinity, which theorem tells that going to apply to find that k? Final value theorem. Okay, solution. By final value theorem, comma, limit t tends to infinity, f of t is equal to limit s tends to 0, s times f bar of s. Okay. So what is f bar s? The given s term, which is pre-operated by L inverse, is nothing but f bar s, that is Laplace transform of some function f of t. This I can denote it by f bar of s. Okay. So now this becomes, which implies this is given already one left side, right side, limit s tends to 0. The pre-multiplication s is cancelled with the denominator containing one s common. That s, see, this s cancelled with one common s in denominator. Okay. So that means I can write 3s plus 1 divided by, after taking s outside, s square plus 4s plus k minus 3. Okay. Now this implies 1 is equal to, after cancelling s and then substituting s is equal to 0, it is going to get defined 1 over k minus 3. From this, k is equal to 4. Now if you substitute here k is equal to 4, what are the poles of f bar s? Because I applied final value theorem, what are the poles? S is equal to 0, s is equal to minus 2 comma minus 2. After s is equal to c, just I will verify. Now what is this function after substituting? K, s cube plus 4s square plus s is equal to 0. So whenever the denominator going to 0 at a value of s, that s value is called pole of the function. Now here s into s square plus 4s plus 1 is equal to 0. So s is equal to 0, left hand side of the s plane. Others s values are obtained by quadratic equation, minus 4 plus or minus root over 16 minus 4ac, 12 by 2a. So this simplifies to minus 2 plus or minus root 3. So minus 2 plus root 3 minus 2 minus root 3, which completely lies on the left hand side of the s plane. Okay. Here all s numbers are real numbers. Just see. Only one dimensional, because s values here, this center point is 0, minus 2, somewhere here, minus 2 plus root 3. How much? Root 3 value 1.732. So minus 2 plus 1.372. So that means somewhere this point, and minus 2 minus root 3 somewhere this point. So this is the left hand side of the s plane. So that's why final value theorem is applicable in this problem, because the poles of s, these are lies on the left hand side of the s plane. Here s plane means only s axis, because all poles are real numbers here. Okay. Second problem I am giving, later you do. (2009) given L of f of t, L of f of t is equal to f of s. Instead of f bar s, it is given capital F of s. 2 times s plus 1 divided by s square plus 4s plus 7, comma, then the initial and final values of f of t are respectively dash. So I am going to find only initial, because final value already I have done. Solution by using initial value theorem. IVT stands for initial value theorem. Limit t tends to 0 f of t is equal to limit s tends to infinity s times f bar s, and this is also denoted by initial value of f of t given by f of 0. Now this is equal to limit s tends to 0 s times s tends to infinity. What is s into f of s? 2 times s into s plus 1 divided by s square plus 4s plus 7. So here both are same degree, then s tends to infinity gives answer constant term, non-zero term. If less by more, numerator degree less than denominator degree, then s tends to infinity problem is going to 0. If s tends to if numerator degree greater than denominator degree, then limit s tends to infinity going to infinity. These are the 3 different shortcut methods. So anyhow, whenever x tends to infinity, s tends to infinity, a variable tending to infinity, in such problems convert all the terms into reciprocal. That means s converting into 1 over s, s square converting into 1 over s square. That means take out the highest s terms in numerator and denominator. These things I have discussed in limits chapter, calculus, common max paper. Okay. So 2s, take out this s from this factor and take out s square from this factor. Remaining terms are in the form of inverse or reciprocal. S square 1 plus 4 by s plus 7 by s square. Limit s tends to infinity. So this is going to become 2. Okay. Similarly, later you check by final value theorem, comma, f of infinity value going to 0, that is limit s tends to 0. Later you check. And some note points I am going to give so that we will wind up this Laplace transform. Make it fast. First one, the necessary condition for LT of f of t exist is integral 0 to infinity modulus of e power minus st into f of t dt is convergent integral, that is finite. This integration should be finite. Next, sufficient condition. This is necessary condition, sufficient condition. If f of t is continuous and limit t tends to infinity e power minus st f of t e power minus at is finite, then the Laplace transform of f of t exists for s greater than a. So whenever Laplace transform of f of t exists, then this integration is finite. That is necessary condition. Whenever these two conditions satisfied, then in such cases the function f of t should exist, Laplace exist for s greater than a. These are necessary and sufficient conditions. Laplace transform of delta t minus a is equal to e power minus as and L of delta t is equal to 1, where delta t minus a is the unit impulse function or Dirac delta function. Okay. Again, this delta function will come in signals and systems. Delta t minus a is the generalized function defined as delta t minus a is equal to 0 for t not equal to a, infinity for t is equal to a, subject to 0 to infinity delta t minus a dt is equal to 1 for unilateral Laplace transform. Integral 0 to infinity. So if the large force acts for a short time, then the product of force and time is called impulse, and the limiting form of this force is called unit impulse function, denoted by delta t minus a. Generally earthquakes happen in the short time of intervals, short time only. Okay. Next, multiple integrals. That is nothing but double and triple integrals. Okay. So just I am giving you procedure how to find double integral, triple integral, and areas, volumes, applications. Okay. To evaluate double integral over R f of x comma y dx dy, comma, the following are the cases. Here R is the region bounded by the curves. F of x comma y is the function to be integrated. One is with respect to x and the other is with respect to y. That double integral is double integral of a function f of x comma y defined over the region R, denoted by double integral R f of x comma dx dy. Directly I am giving how to evaluate. There are three cases. Okay, according to the region bounded by the curves, that limits. Following are the cases. 1. Region R is bounded by the curves y is equal to phi 1x and y is equal to y is equal to phi 2x, and the lines x is equal to a comma x is equal to b, that is x limits are constants. And R is divided into vertical strips PQ, denoted by PQ, vertical strips PQ. Just see the diagram. Y is equal to 5x, or this is y is equal to 5 to x, like this. And this is two vertical lines, that is because of x limits are constant. This is x axis origin, y axis. This straight line is x is equal to b, and this is x is equal to a, and this is y is equal to 5x, and this is y is equal to 5 to x. And this part is called shaded part, is capital R. Okay, so in this I am taking two standing lines with small distance between these two standing lines. This is denoted by, generally are called vertical strip PQ. So that means the purpose of introducing or drawing this vertical strip is, first you integrate along this strip, that is first with respect to y between the y limits, and then slide or move this strip from x is equal to a to x is equal to b. That means next integration with respect to x between the limits x is equal to a and x is equal to b. Okay, here integrate first, because this is a definite integral, final answer should be a number only, not in terms of x and not in terms of y. So that means always integrate first with respect to a variable having the limits in terms of other variable, and integrate last with respect to a variable having constant limits, constants. First with respect to y, first integrate, here integrate first along the vertical strip PQ, that is integrate first with respect to y between 5x and 5 to x. This is the procedure how you evaluate one by one integration. And then with respect to x between a and b, lower limit of x is a, upper limit of x is b, lower limit of y is 5x, upper limit of y is 5 to x. So sometimes without strips we cannot evaluate the double integrals. That will come in the next topic, change of order of integration. Okay, for understanding purpose only that I have drawn that strip. So therefore double integral over R f of x comma y dx dy is equal to x is equal to a to b keeping inside y limits y integration, y is equal to phi 1x, phi 2x, f of x comma y, dy and then dx. So this is the way to evaluate definite integral in the case 1. Keeping outside x limits, keeping inside y limits, because inside integrate first and outside integrating last. Similarly, I am giving directly case 2, case 3 how to evaluate. Okay. Second case, region R is bounded by the curves x is equal to phi 1y and x is equal to phi 2y, and the lines y is equal to a, comma y is equal to b. That is, R is divided into horizontal strip PQ. Earlier is vertical strip PQ because y limits functions of x. Whenever x limits are functions of x, then you divide the region into horizontal strips. Here, a curve like this, another curve like this, and y limits constant means they are parallel to x axis horizontal lines. So this is y is equal to b, and this is y is equal to a, and this curve is x is equal to phi 1y, and this is x is equal to phi 2y. So here somewhere, either middle of the location, middle of the region, or bottom of the region, top of the region, left of the region and right of the region, anywhere you can take strip. In horizontal, middle, top, bottom, limit should not be changed. Similarly, while considering vertical strip, you can take at middle of that region or left of the region, right of the region, end, beginning of the region, last of the region. Your limit should not be same. Whenever it changes, you split into that number of regions. If there is a change, then your region is divided into two parts. If there is a two changes in either upper limit case or lower limit case, then you divide the region into three cases, like that. Just properties of definite integrals, property. So this is the region R. R is the region. Here integrate first with respect to x, because x limits are functions of y, between phi 1y and phi 2y, and then with respect to x, y, between a and b. So this is the procedure to evaluate in the case of considering X limits functions of y and y limits functions of x. X limits functions of y and y limits are constants. Just a moment. In this case, y is equal to a to b, x is equal to phi 1 y, phi 2 y, f of x comma y, first dx and then dy. This is the way to evaluate. Always integrate first with respect to a variable having variable limits and then with respect to a variable having constant limits. This is the order of the preference of integration.